to give you an overview of what today and this weekend's going to look like. All right, today we're going to keep moving forward. We're going to cover 3.7, 3.8, and 3.9, right? Our 3 lessons that we said we were going to cover a day, right? We're going to try to cover all 3 of those in class. And then this weekend, right, you're going to cover a couple lessons to finish up Unit 3 and a couple lessons to finish up Unit 4 here. Okay, and what I will do is I have that video recording already ready to go, so I will post that tomorrow morning. All right, I'll post that tomorrow morning, and I'm just going to post that as a normal YouTube link, not as an ed puzzle, so there's no pressure for you as to when you want to watch it or if you want to break it up or anything like that, because I know with ed puzzle it makes you watch everything fully through. So I'll just post it as a regular YouTube video. All right. And I say this in the video, but I'll say this again. All right. When you're going through it, I really suggest that you break at the end of Unit 3. Okay. Because you're going to be responsible for finishing Unit 3 and then starting Unit 4. All right. So that's kind of going to be where we're at in terms of this weekend. Okay. All right. Any questions here before we get rolling? Any questions? All right, awesome. So then if we get started here, as we get started here, there we go. All right, like I told you, we're going to cover 3.7 today, 3.7, 3.8, 3.9. All right, and 3.7 looks kind of nasty because it has 3 quizzes here. All of them, yes, are mandatory, but it's just because they broke it up into specifics. So we're going to look at evaluating exponential expressions, evaluating logarithmic expressions, and then evaluating logarithms in general. Okay, so those are going to be the 3 quizzes for this unit. All right, in 3.8, we'll have 1 quiz, and then in 3.9, we'll have another quiz. All right, so that's what's getting assigned today for you to finish in order to keep on track there. All right, so if we look at 3.7 to start with, all right, we're going to talk about the properties of exponents and logarithms. All right, that's obviously the name of the game of this entire unit here. Okay, so we kind of have a basic understanding of what they are now, and we know that exponential and logarithmic functions, okay, they undo each other here. Right, we talked about their specific functions. There's a couple specific logarithmic functions that are more popular than others, right? And that would be our log base 10 and our log base e, otherwise known as our ln function. Right, so that's our natural log is ln, and then our common log is our log base 10. Okay, and so if we move forward here, we've got to take a look at some of the properties of these two, and we're going to start with exponential expressions here. Okay, and hopefully we can remember these, and if not, then this is a great reminder. All right, when we're multiplying, okay, when we multiply exponents, okay, it's like adding them together, as long as they have the same base value, right? So if I have base to the m and base to the n, right, what happens is since they're multiplied together, I'm adding just the exponents. All right, so what that looks like is if I have 5 to the power of x and 5 to the power of 3, that's like saying 5 to the power of x plus 3, right? Or if I have 4x times 4 to the power of 5x, right, that would get me x plus 5x as my new exponent, or 6x, right? And of course, obviously this works with values too here, right? So if this was just 5 to the second and 5 to the third, obviously these guys added together would just be 5 to the fifth. You could calculate that out in using your calculator here. But obviously we're doing a lot with solving our exponents. We're doing a lot with solving our exponents. So again, we're going to have mostly our variables up there. All right. So again, when you're combining, those rules stay true for basic properties, right? And I can go back there, right? Basic properties. So hopefully you noticed that we have x plus 3, right? We can't just make that 3x. So again, it has to be similar terms getting added together. All right. These are both x to the first degree. So that's why we can combine them and make 6x, right? So our basic algebraic skills here. All right. And then I skipped over one here on accident. All right. Division law. All right. Our division law. We have two things with the same base and they're divided. If we have two things with the same base and they're being divided, right, what we actually can just do easily is subtract the exponents. All right, so if I've got 3x over 3 to the power of 4, that just is 3 to the power of x minus 4. Same thing here, 2x over 2 to the power of 3x. I'm just going to do x minus 3x, which gives me a negative 2x, right, negative 2x. So again, basic algebraic skills once we understand that, hey, we can combine these exponents since they have the same base value. Okay. Now what we can do here is our product law, quotient law, and our power law. So when we're looking at our product law, okay, what that means is if I have two quantities, right, both in parentheses, and they're being multiplied together, right, and I have an exponent on the outside, I'm going to bring that exponent to both of them, right? I'm going to distribute that exponent. Okay, so 2 times 8 to the power of 3, that's like saying 2 to the power of 3 times 8 to the power of 3. Okay. Our quotient law is similar. If we have a over b, right? If I have a over b to the power of n, I can again distribute that n to both of them, right? So for 4 over 7 raised to the power of 6, that's like saying 4 to the power of 6 over 7 to the power of 6, right? So it's undoing the combination that we just talked about on the last slide. All right, and then for this one here, the power law. This is if you have something, so this is b to the power of m, and this thing is then raised to the power of n. All right, so this is b to the power of n, and this quantity is raised to the power of m. All right, so what we end up doing here is we multiply, right? We multiply our two variables together. All right, so we can multiply our two variables together. So this is 5 to the power of 4, and this quantity is raised to the power of x, so that's going to be 5 to the power of 4x. Same thing other way, 9 to the power of x, that quantity is to the power of 7. We now have 7x here. Okay. The multiplication and division laws for exponential expressions can be used when the expressions have the same, and this is super important, the same base value, the same base value. Okay, so we can combine things together on that first slide when we have the same base value. Okay, that's the key there. All right, and then again, taking a minute to review those laws is going to be super important here. Okay. All right, and then working through these problems here, I'll let you guys try these on your own, but it's some basic review problems, mostly, or a little bit of intro if this is brand new to you. Okay, but take a minute to really work through these problems here. And something I just want to point out is just because they have exponents, right, you have to double check that they have the same base when you're trying to combine exponents, right? Like we just said, that's super important. All right, some of these, or on your quiz, right, you might not be able to combine them, right? You might not be able to fully combine them, and that's okay, right? That is okay. But you have to make sure that you're not trying to, fit something to a formula just because we have them. All right, so again, these are having the same base, so that's a great step, right? They have the same base, and then we look and, oh, they're multiplied together. So because it has the same base and they're multiplied together, we have a rule for this, right? If these guys were added together, we don't have a rule that we talked about where same bases raised to the exponents are added together. So maybe you wouldn't be able to simplify them. All right, so really remembering that we're not trying to just fit things there. All right, if we look at these guys here, all right, so this is that first problem, so I guess it really wants us to do this first problem, okay? So This is asking us for all the equivalent expressions below. All right, and I really like this because take a look. All right, so if we look at 4 squared, okay, 4 squared, that's like saying 4 times 4. All right, and that will give us our value of 16. So this first answer here, that's an equivalent expression, right? We could just write this as 16 times by 4x, right? 16 times by 4x. That's fair, right? Then when we multiply these two together, right, it's like adding. It's like adding. So it's going to be our 2 plus x. It's going to be our 2 plus x. Or, right, we know we can move them around because it's just an additive property, or e to the power of x. Or I'm sorry, x plus 2. Wow, e to the power of x. We can do 2 plus x or x plus 2. All right, and then the rest of these are obviously not correct either because they simplified something that you couldn't simplify, or they didn't add the exponents correctly. All right, but there's multiple ways of looking at it. All right, and again, when we move forward here, we're going to talk about how to solve them, right? And it's going to be whatever is easiest for you to solve, whatever is easiest for you to solve. All right, so then I'll obviously let you guys go through and work backwards on 2. All right, and then same thing, working forwards in this this next problem here for 3 and then 4. Okay, so trying to combine them and see what happens, right? And this is a perfect example of, look, they don't have the same base value. So you have to be careful with what properties you want to use. They don't have the same base value. So you have to be very, very careful here. All right. Now, if we look here, we go to our logarithmic expressions. Okay, we look at our logarithmic expressions. All right, so I know this was a little bit of an introduction for us. So let me remind you here that if I have an exponent, right, I can undo that function, right, or the inverse of that function is using this log here. All right, so if we use the same letters in both of these expressions here, all right, I have log base b of a, right? So that's how we could say that is log base b of a equals my value of c here. All right, and what that's going to end up meaning here is that b, my base, raised to the what power is going to give me my value of a, right? And that's how we evaluate this expression, right? B to the power of what will give me my value of a. All right, so if I look here, they already solved these for us here, but we can still ask the same question. 10 to the power of what is going to give me 100? 10 to the power of what will give me 100? And obviously that's 10 to the power of 2, or 10 squared will give me 100. All right, same thing over here. 3 to the power of what would give me 81? Well, 3 to the power of 4 gives me 81. All right, so that's how we can rewrite these expressions here. Okay, so again, understanding that their inverse functions is going to be super helpful as the first property here. All right, so what that means is they will undo each other. So if I have my log function, right, and I have my log base b, all right, I have my log base b multiplied, log base b of b to the power of n. All right, what they're saying here is that your log and your exponents cancel out and you're just left with this value of n here. Right, you're just left with this value of n here. And let's take a look at it. It says why, okay? Because b to the power of n gives you b to the power of n, right? B to the power of what would give you b to the n? Answer is b to the n, all right? So these functions, right, these functions undo each other, and essentially they cancel each other out here, right? They essentially cancel each other out here. All right, so if you have log base b of b to the n, right, the next step you would just replace it with this exponent here for n. All right, and then same thing here. I have b to the power of log base b of n. All right, and what we could do there is we could take the log of both sides if we needed to, and then we could simplify down from there. All right, we could simplify down from there. And again, log of b and power of b, right? Those guys would cancel using this new property that we know here. Those guys would cancel. So we're left with log of b of n equals log of b of n. All right, so that's saying those guys are equivalent expressions here. All right, they're equivalent expressions. All right, so again, essentially what happens is if you have, again, log base b and you are evaluating it for b of n, those guys cancel out. Same thing, if you have b raised to the power of log base b, those cancel out, and all you're left with in both of those cases is the exponent for the power of n. Okay, so understanding that we can undo each other is great, right? Those products undo each other, but now you got to look at the different properties of just the logarithmic expression itself. Okay, so the first property here is our product property, meaning log base b of two numbers multiplied together, I can separate them out into addition, right? So right here I have a times d, so if I want to separate them out here, I can write this as log base b of a plus log base b of d. All right, so hopefully kind of parallel, right? You can find some parallels between these properties and the exponential properties, right? So again, if they're multiplied together, it's like adding them, right? It's like adding them. So log base 12, right? Log base 12 could get split up into log base 3 plus log base 2. Log base 3 plus log base 2, right? Or since we know that to get 12, we could also have 6 and 2, this could also be equal to log of 6 plus log of 2, right? It could give you multiple answers there. All right. Example 2 here, if we have log of 5 plus, or sorry, ln of 5 plus ln of 7, all right, they have the same base value, right? This ln, and then you would do 5 times 7, which gives us 35, right? So we could simplify this larger expression down into just ln of 35 because it's 5 times 7. All right, and then for the last one here, we have log of 2 equals 21, right? So we can set that equal to the two values that we can multiply together and get 21, and that's 3 and 7 here. All right, so 3 and 7. All right, and paying really close attention to that whatever your base value is in your combined function, whatever your base value is in your combined function, it has to be the same in your separated functions. So this one was log base 10. That's how both of these were 10. Both of these were log base e, or this ln function, which is why in our combined product we had ln. All right, and then finally here, this was log base 2 and log base 2, so we could combine them to make log base 2 of 21. All right, again, the key there is they have to have the same base value. If this is not the same, you cannot combine them, period. If they're not the same, you cannot combine them using that method. All right. And then we have this thing called proofs, right? So we know these product properties, okay? And we can now, instead of just accepting them as yep, Miss Judy said it works, we can do this thing in math called proofs, all right? And then what proofs do is they use laws or definitions that we already know in order to verify that a fact or a property is true, okay? So for this one here, we can use our logarithmic expressions looking at our first property here. So if we were to look at the proof here, okay, if we were to look at the proof here, we could write it as this different definitions here. All right, we could write it as this different definitions here. If we used our substitution law, right, we could use this product property. If we use our multiplication law that we just learned, we could use that property. All right, if we looked at inverses, we could do that, and then our substitution. So regardless here, there's a lot of ways of proving that this is true, and how this is helpful to you is that it's really a good way to, if you forget how something works, if you forget how something works or why something works, one, you can always plug in values and then check in your calculator. Okay, that's always a good one. And then two, you can do this thing called proofs, right? You can use proofs to verify that what you came up with is true. Okay. Moving forward here, similar to addition, right now, if we subtract our individual logs, we get this combined A over D, or we get this combined new fraction here. Okay, we get this combined new fraction. So we have log of A minus log of B, right? Key being that they have the same base value. Key being that they have the same base value. Here it's base 10, base 10. Great, so these guys can get combined into this fraction of 2 over 5, right? 2 over 5. And yes, of course, order does make a deal here. So it has to be whatever is being subtracted is now the denominator. All right, so we've got ln of 6 minus ln of 2, right? They have to have the same base value, which they do. And then we can combine them into this fraction, right? And then from there, if you can simplify down further, do it, right? So we've got ln of 6 divided by 2, or 6 over 2. We can then simplify that down to ln of 3. All right, and last example here, we've got log base 5, log base 5. All right, so we can combine 90 and 9, and then simplify that down to log of 10. All right, and if you want to look at the proofs, right, all they did here was they replaced using the definitions of our exponential functions that we know, right? They replaced using the exponential functions that we know. So instead of saying a, all right, they said b to the power of p, because that's what this expression would stand for here. Log base b of a, we could replace this using our exponential expression that we know, b to the power of p equals a. Right, so that's all they did here in order to, again, prove these. So they just replaced using what they know and combined from there. All right. Now looking at if we have logs to powers, that's one of my favorite ones, okay? So if we have a log base b, and the inside property here is a to the power of something, right? So this is a to the power of d. What actually happens is we just bring this exponent out in front, and that is now a new constant that we multiply by. So look, we brought that exponent out in front, so now it is d times log of b, base b of a. All right, log base b of a. And so all we did was we carried that exponent out in front. So very easy. Bring that 2 out in front. We now have 2 log of 5. All right, 3 to the power of 4. We bring that 4 out in front. We've got 4 ln of 3. All right, and then finally here, if we have a 3 out in front, so 3 times log of 6 of 4, we can combine that by saying log of 6 of 4 to the power of 3, right? We just do the opposite. We bring that 3 back up as an exponent there. Okay, and again, if we wanted to look at proving as to why these were true, right, we could rewrite our expressions here. And all this is saying here is we have multiple ways of proving that this is true here, okay? And all it's doing is saying that if we had this property, it would be like saying log of a times a times a times a times a. And since we know this property here, it would be like saying all of these individual ones get added together, right? Since we know that if we multiply, we can add those individual logs together, right? And when we add something together, all we're doing is increasing the value out in front, right? We're increasing that constant value or a coefficient value out in front, right? So we can just easily simplify that by just saying d times log of b of a, all right? And so this chain of equalities or equal expressions, right, all of these are equal to each other. They end up proving why this expression here is true. Okay, then if we look at, of course, we've got some special cases here when log is equal to 1 or log is equal to 0. All right, so again, as always, if you have log of 1, right, regardless of the base here, okay, that's saying exponent equals 0, right, because that's saying 2 to the power of 0 gives you 1. 10 to the power of 0 gives you 1. E to the power of 0 gives you 1. Hopefully not too terribly difficult here. All right. And then if we have things that equal 1 here, all right, or I'm sorry, if it's equal to 1, all right, that should hopefully be very simple. That's saying 2 to the power of 1 gives me 2. 10 to the power of 1 gives me 10. E to the power of 1 gives me E, right? So some basic things that are still worth addressing here. Okay, so the properties of logarithmic expressions are related to the related to the laws for exponential expressions, right? So there are some similarities here, right? And you can look at that again, the multiplication, addition, division, and subtraction. All right, more practice problems that you guys can work through here, and then check them up with these check your understanding questions here. All right, I don't want to give away all the problems here, but basically every time you hit a new check your understanding, that's your new little quiz here, right? So that first one that we checked, that would be quiz 1, right? And then from that check your understanding to this check your understanding, this is quiz 2 here. All right, and then this next little section is what's going to be on quiz 3 here. All right, and this is looking at or starting with this change of base formula. Okay, so we've been dealing a lot with everything has the same base, and that's wonderful, right? We can change it, we can combine it, right? But what happens if it doesn't have the same base value here? All right, and if it doesn't have the same base value, all right, or if it has a base other than 10 or E, right? Something we can't plug into our calculator. Well, what we can do here is we can rewrite our expression using this new property here. All right, we can do this thing, and it's called the change of base formula. It's called the change of base formula, lo and behold, because we are going to change the base of our equation here so that we can either cancel things out or we can plug it in our calculator. All right, and what this looks like here is if I have log of b of a, right, log base b of a, all right, that's my expression here. I can change it to log of this new base c of a over log base c of b, right? A couple things I need you to notice here, right? It doesn't really matter. It doesn't matter what log base function you change both of these to, as long as they are the same, right? So if you want to go log base 10 over log base 10, fine, as long as it's the same. Or you want to go log base 10, or I just did that one, sorry, log base e over log base e, or our ln functions, fine, it doesn't matter as long as it's the same base here. Okay, and then obviously when you're changing expressions here, it wouldn't make sense for you to change this to a log base that you don't have in your calculator. So typically when we're doing this change of base formula, we're dealing with either that common log, our log base 10, or our natural log, which is that log base e or our ln function. Okay, and then obviously notice that a is in our numerator and our base value is in our denominator. So if we take a look at this, we have log base 6 of 3. All right, so we take our a value, put that in our numerator, our b value, and put that in our denominator, and then we've decided for this one to change it to log base 10 over log base 10. All right, and then all we would have to do here is plug into our calculator log base 10 of 3, log base 10 of 6, or just log of 3 divided by log of 6. Because again, the log that's on your calculator is log base 10. All right, similarly here, right, we can do this for log of 2 of 7, right? So again, writing our a value numerator, b value denominator, and for this one they decided to go log base e, right? They decided to go log base e or our ln, right? And again, it truly doesn't matter as long as you have the same base on the top and on the bottom. All right, and if you took a second on your own, you can look through this, but basically all they're doing is using expressions that we already know or properties that we already know in order to prove as to why this is true, or in order to make our expression on one side turn into our expression on the other. All right, so that's all they're doing here is using things we already know in order to make sure that you believe that this is true. okay? So then again, you can choose either common log or natural log. So if we look here, all right, common log answers there, natural log answers there. It's the same exact value, right? You got 16/8 for both of them. They're the same on the top and the bottom, same on the top and the bottom, so it doesn't matter. It's going to give you the same values, right? It's going to give you the same values if you plug it into your calculator, all right? So there should be no issue with whatever you want to choose. That's kind of a personal preference there. All right. So the only logarithms you can find with the calculator are the common logarithms and the natural logarithms, right? So common being our base 10, natural being our base E. All right, common being our base 10, natural being our base E. All right, and for this one here, of course, you're gonna have to change this into a formula that you can plug into your calculator. Or you're gonna have to plug it into your calculator for most of these. Or if you notice here, there are a couple that they try to trick you on. Look, and get e to the power of ln of 9, right? Well, e and ln cancel out, and I'm just left with my exponent, right? So I'm just left with my exponent. So they try to trick you on a couple of these. So make sure that you do those correctly there. All right. And for the other ones here, these are, you're going to have to do your change of base formula. Or you're going to have to do your change of base formula if you can't just directly plug it into your calculator. All right, now let you, of course, try those out. Same thing here, evaluating the expression. All right, you've got your different log functions. All right, you've got your different log functions. So using the change of base formula in order to evaluate them, or understanding the principle that they undo each other, right? They undo each other. So if I've got e to the power of ln, again, e and ln will cancel each other out. Same thing as if I had ln and my expression had an e value. Those guys would cancel each other out. All right. So then looking at our study sheet here, of course, this is going to be super important. Our law of exponential expressions, it's summarized really nicely here in this table. And then looking at our different rules of logarithms, right? That's going to be really, really helpful for you moving forward, okay? And then, of course, understanding the relationship between exponents and logarithms, all right? Understanding that relationship is another key value there. Okay. And then the final thing we talked about was our change of base formula, right? Our change of base formula. And regardless of if you do base 10 or base E, when you plug it into your calculator, you're going to get out the same values. So when you do your change of base, it truly doesn't matter. It's whatever your preference is. Okay. So then looking at our expressions here, all right, looking at looking at our checkup here. Okay, we gave you the change of base formula. Okay, so you don't have to go hunting for it here, right? But some of the other properties, right, if you don't know them offhand, having that study sheet might be super helpful here. Okay, and I love these questions. Determine whether the expressions are equivalent, right? If they're equal to each other, if you can combine them in the way that you think that you combined them, okay? So that's going to be really, really helpful and important for you to take a look at. All right, for these guys here, simplify the expression as much as possible without a calculator, right? So what can you combine? If you can combine things, what would it look like? All right. And then finally, obviously evaluating the logarithm. So evaluating means get an actual value. Get an actual value. So this is going to be talking about obviously our change of base like formulas. All right. Our change of base like formulas. Because you can't plug in your calculator log of 4 of 13. Okay. So then, of course, you have 3 quizzes here, but it's naturally broken up for you in the study here. So the first one, obviously, only dealing with changing our exponential expressions into different forms. The next one dealing with changing our logarithmic expressions into different forms. And then this final one was on evaluating those logarithms, right, using that change of base like formula. Okay, so hopefully not too terribly difficult there for 3.7. All right, then if we go to 3.8 here, we're dealing with solving exponential equations. Right? We're dealing with solving exponential equations. All right. So we looked at all of those different properties and how they relate to each other. So now what we can do here is work on how do we actually solve our exponents now. How we actually solve our exponents. So if we look here, if we just have b to the power of x equals d, all right, all we have to do is we have to isolate the variable by taking the log base b of both sides. Okay, so what does that actually look like here? We just change it, right? We just change both of these expressions here to something log base b, all right? Our log base b, all right? And yes, it is important. It's based, it's our log base value of our base here, right? So this is 10 to the power of x, right? That's our base. So we change it into this log base 10 of 10x and log base 10 of 190, right? And the reason we do that here is because when we simplify, okay, we can use this property here that our log function, if it has the same base value as the value inside, right, those can't cancel each other out. So over here, log base 10 with 10x, right, that's going to cancel the 10 value out. All right, that's going to cancel our 10 value out. So we're just going to be left with our exponent here. So we have x is equal to log of 10 of 190. All right, and we can then plug into our calculator log 190. So all you have to plug in log base 10 of 190, hit enter, and it's going to give us this number right here. Okay, so it'll give us this value right here. Right, and in general, Apex likes to simplify things to 2 decimal places, so this would be 2.28. All right. Then here, if we have a base e, right, so it's no longer a base 10, it's a natural base, right? We're going to have to deal with, obviously, a natural logarithm, but we're going to follow the same process. We take the log of both sides, log base e, all right, log base e, again, because we have this as a base e value here. Okay, so we know that those cancel each other out, so we're just left with x is equal to ln of 8. We can plug that directly into our calculator, and we're given the answer of 2.08. Okay. Then, of course, what happens if we don't have a nice base that we can cancel out here, right? It's not a 10 or a natural log. Okay, so we already know how to solve this one here, but now we're gonna focus specifically on it. All right, we can do our change of base formula. All right, we can do our change of base formula. So if we start off, if we take the log base b, right, we're gonna start the same way, log base b of both sides, because we've gotta get rid of this exponent or bring this exponent down here. So we're gonna have log base 3 of 3x and log base 3 of 0.25. All right, so again, log base 3 and 3 cancel when we've got x is equal to our log base 3 of 0.25. All right, this is where, okay, we don't know how to plug this into our calculator, right? We can't plug in log base 3 of 0.25. So what we can do here is we can do our change of base formula. We can do our change of base formula. So we write this as log base either 10 or base e, doesn't matter as long as you're consistent. All right, you'd write this as log base 2.25 over log base 3. All right, so log base 10 of 0.25 and log base 10 of 3. All right, then we can plug both of these expressions, since they're in log base 10 form, we can plug them into our calculator and actually solve for a value here. Okay, so then using the power property here, okay, we can then use our power property and again, look at things with bases other than just 10 or e. All right, so what we can do here is same thing. We can take the log of, we can take a log of both sides, but this time, instead of taking the log base 3 that would cancel out this 3, right, we could take the common log of both sides. All right, and once we take the common log of both sides, we can then use our power property, right? We can use our power property, which means 3 to the power of x, right? We carry that x out in front, right? So we now have x times log of 3 is equal to log of 0.25. All right, then if we isolate the variable, as step 3 says, right, that's dividing by log of 3 on both sides. And lo and behold, we are left with the same expression that we started with on the last slide, right? So we're left with the same expression from the previous slide here. Okay, so a pretty good way of doing either of those, right? It's really your preference. Okay, it's really your preference as to what you would like to do here. Okay, so then moving forward here, if we look at a more complicated example, all right, so first we might have to divide by something, or we need to isolate the variable that we're trying to solve for. So first we got to divide by 8, then we have 2 to the power of x equals 15, right? So then we can take the log of both sides here, right? Log base 10, log base 10, right? We can carry that exponent out in front and use our product property. In order to bring that x out front, we divide both sides by log of 2, and there you go. We have something that we can actually now plug into our calculator and evaluate for that expression. All right. Again, the trick was to get rid of that constant or that coefficient out in front here so that we could just isolate our exponent. All right. So in order to solve exponential equations, you need to use logarithms. Okay, we need to use logarithms. And again, that's because they undo each other. Okay, they undo each other. So that's going to be super important here. All right. And then regardless of what we start with, as long as we get it to the same place, right? We can get it to the same place. We can then follow the same steps. Take the log of both sides, cancel out if you can cancel. If not, use the power property, bring that value down, and then solve for both sides here. Okay, so again, these are going to be a little bit more involved. It's not just going to be right off the bat. So again, use your change of base formula, right? So you're going to have to use an ln here since this is an exponential expression, right? But again, these are really, really good for you because you need to make sure that you are able to plug them in your calculator correctly, all right? That's the biggest mistake here is calculator errors. So make sure you go through them and really try these problems out here, okay? So again, the first two are some basic examples here. This one, E and ln are going to cancel. This one, you're going to have to use your log base 10 and your product property. Okay, this you're going to have to isolate and this one too, you're going to have to isolate both of these before you start and then use the same process of taking the logs of both sides. All right. So then if we look at this chess problem that they would have introduced to us in the intro, right, but I kind of skipped over it here, is we have this inventor of the game of chess, and he's said to have asked for the following reward: a grain of rice on the first square of the chessboard, 2 grains of rice on the second square, 4 grains on the third, so on and so forth, right? So he wants 2 to the power of x, right? He wants 2 to the power of x. All right. So we're able to keep in mind that this is our expression here. So it tells us how many grains there are in x plus 1 piles, right? X plus 1 piles. So for example, here, if you look at our 10th, right, our 10, this is telling us how many grains of rice are in the 11th pile, okay? Are in the 11th pile, using, of course, this expression here. Okay, using that expression there. All right, so if we were to do this here, we have a couple questions here. All right, although it starts off very small, we obviously know that dealing with exponential functions, they're going to go really quickly. All right, so if we looked here, which is the pile that will have 1 million grains of rice first? All right, we can look at which pile weighs more than 1 metric ton, and then which pile would be as large as the Pyramid of Egypt. Okay, so if we look at the first question here, which is the pile that will have 1 million grains of rice? Okay, all we have to do is easily take this expression and set it equal to 1 million and then solve for that, right? We solve. So we take the log of both sides, use that power property, bring it out front. We can divide, and we're left with 19.9. Okay, so what we have to realize is this rounds up to 20, right? Again, using logic, we don't have 19.9 piles, right? We're only doing at whole intervals. So this is 20. Okay, this is 20. And then we have the 20, then since we know that this is talking about in general, right, instead of this being the x value, talking about that pile, it's talking about the pile in front of it. So when we're dealing with x equals 20, it's talking about the 21st pile. Okay, the 21st pile. All right. If we look at the next question here, okay, which pile will equal or weigh more than this? Well, if a metric ton is equal to 1,000 kilograms, all right, it has to weigh this much here. All right, so, and the reason we know that here is we said each metric ton of rice contains about 43 million grains. Okay, so simple. It's going to be the exact same process here. Okay, the exact same process. And then once we've got it as our value here of 25.4. Okay, we round that up saying the 26th pile, and we now know that, again, we have to add 1 onto our x value in order to get to our new pile. Okay, then finally, that last question here. Okay, that last question. If we were to look, which one would be larger than the Pyramid of Giza in Egypt? Okay, so if the volume of the pyramid is approximately this many cubic meters, right, and 1 cubic meter is this many grains of rice, right, we would multiply those two together. So we simply need this large exponent we need of grain of rice here. Okay, and this is written in scientific form to indicate a really, really large number. Okay, so then looking here, the piles that will be as large as the Great Pyramid here, all right, we just set it equal to each other. Still, same thing, we can take the log of both sides, all right, and we can use our power property for our left side here. We take our power property for our left side, we divide both sides by log of 2, and we can then put that into our calculator, figure out, okay, it's going to be the 48th pile. All right, something I want to notice, or I want to point out here so that you can notice it, all right, is this here, we do not simplify. This is a way of expressing one value, okay, and you'll learn more about this in your physics course, but this is something my sophomores here worked a lot with last year in chemistry class here. So writing in this scientific form here, so don't let that freak you out. It's just representative of a really large number here. Okay, so exponential growth, of course, we know it grows really, really quickly. It might take a little bit of time to start building up, but once you get into that really curved part of the growth function, it grows rapidly. All right, so then moving on here to our study guide. All right, moving on here to our study guide. All right, so again, we were solving those exponents in different forms, and really the base here was get it down to this b of x is equal to some value, right? Get it down to b of x is equal to some value. Once you do that, we then take the log of both sides, use our different properties to get x by itself, and then we could just plug into our calculator here. All right, so that's really what essentially happens is if we get it by itself here, we get it by itself, right? We put log on both sides, and if it's base 10 or base e, right, it's even easier because those bases cancel out, right? Those bases cancel out. If it's not, right, we have to bring that exponent out in front and then do our division here. We have to bring that exponent out in front and do our division. Okay, and then the rice problem was just more of solving the same exact problem. Okay, solving the same exact problem here. all right, and understanding what it's asking you to do. All right, so looking at our checkup here. All right. It is a lot of problems, right? So again, really working through all of them, trying to get into, again, trying to isolate that exponent on one side, using your log functions on both sides, and then simplifying in whatever way is possible for you. Okay, and again, they are really specific with this, so make sure you're reading your instructions. Round your answers to 2 decimal places. Okay, 2 decimal places. That's going to be super important here. Okay, so for 3.8, we have 1 quiz. All right, so right now we've covered 3.7, 3.8, and then the final guy we're going to talk about here with the last 30 minutes of class is 3.9 here. All right, so we just worked on solving exponential equations, right? So naturally, our next progression is going to be solving our logarithmic equations, right? And hopefully, again, you're going to find a lot of parallels in this little unit here. All right. So basically, hopefully you've got some bells ringing in your head here that we're going to have to undo our log functions. So we're going to have to take things and use our exponential properties. So if we look at this value here, right, it's saying log base 8 of x equals 3.1. So what this is saying is 8 to the power of 3.1 equals x. All right, 8 to the power of 3.1 equals x. All right, and this one here is just straight understanding the relationship between log and our exponent. All right, so if you are left with a problem like this here, if you're left with a problem like this, you just rewrite it. 8 to the power of 3.1 equals x. Put this into your calculator and solve. Okay. Again, looking at a summary of this. Okay, so we're using the definition of our logarithm to write it in exponential form, and then we just plug it in a calculator. So log base 2 of x equals 14. So that's saying 2 to the power of 14 equals what? Right, and it's this really large number for this example here. Okay. So then for problems with natural log here, with natural log, okay, lo and behold, you can do the exact same thing here. You just have to remember that ln is log base e, right? So this is actually log base e of x equals 4. So that's saying e to the power of 4 equals x. E to the power of 4 equals x. Evaluate. Okay. So then what happens if we have a value out in front, right? Well, we have to isolate. We have to isolate our logarithmic expression by itself on one side. So if we have 10 times log base 5 of x equals 3, obviously we've got to bring 10 to the other side. So we divide both sides by 10. All right, and then we are left with our logarithmic expression here, and we can just rewrite it using our definition. So we're going to say 5 to the power of 0.3 equals x, or x is equal to the power, or sorry, 5 to the power of 0.3. We plug that directly into our calculator, and we can get out a value here rounded to 2 decimal places. All right. If we have a little bit more complicated, right? We have a constant out in front and we have a coefficient. Obviously, we have to move our constant first, so we subtract 6 by both sides. Then it's the exact same process. Divide by 4. We use our definition. ln is log base e, so we have e to the power of 4.25 equals our x value, and we can solve from there. Okay. So to solve a logarithmic equation, you need to use the definition of, logarithms. All right, sorry. You need to use the definition of logarithms. Okay, and that definition of logarithms is showing you how logs relate to exponents, how logs relate to exponents. Okay, so you're just going to use that to then solve there. All right. Of course, really great problems here, and I'll let you work these on your own here. So if I have log base 3 of x equals 1.5, again, this one's already simplified, so we just rewrite it in that form, 3 to the power of 1.5 equals x. All right, making sure you plug these in your calculator and double check your mathematics on that one. All right, so this one is simply rearrange, okay? Simply rearrange, understanding ln is log base e. This one we have to obviously get rid of this coefficient first, and then this one has a constant and a coefficient, all right? But a natural progression throughout there, okay? Now, if we take a look at the earthquake problem that we talked about, I believe that was in yesterday's lecture, okay? If we talk about the earthquake problem here, okay, we have this expression, and when we originally talked about the earthquake problem, right, the way that we talked about solving it was plotting it on the graph, finding where the output value, right, where our y value gave us 3, and using that x value. Okay, well now we understand, or we have a way of understanding how to just solve directly for this x component here. All right, so again, reminding ourselves that Rx is the magnitude of the earthquake on the Richter scale. X is the energy of that earthquake in this thing called kilowatt hours, right? Just our unit of measurement. So if we look here, right, it was asking us to figure out what, how much more energy an earthquake of a 3 magnitude has than a 2 magnitude. All right, so we had multiple steps to this problem. And the first step for us was, okay, well, in order to figure out how much more, we have to figure out in general how much energy does an earthquake have when it measures a 3 on our Richter scale. Okay, so we had to figure that out first, and then we were going to take the difference between the 3 and the 2. All right, so with that being said, all we did was we replaced our Rx value here with a value of 3. Right, so we replaced our Rx value with this value of 3, and now we have an expression here that we can solve. So first, we've got to get rid of this constant. So we're going to subtract the constant on both sides. Then we're going to get rid of this coefficient by dividing both sides by our 0.67. Okay, then we have a value is equal to our logarithm function. Okay, well, we can just use our definition here. So if it doesn't have a base value, remember that's log base 10. If it doesn't say base 10, or sorry, if it doesn't say anything, it's log base 10. All right, so we use our definition here, and that's saying 10 to the power of this 2.2985 is equal to our value inside our expression. All right, so that's going to be equal to 0.37x. All right, and before we plug this into our calculator here, we're going to divide both sides by that coefficient out in front, and that's what we're going to plug into our calculator. All right, and it's going to give us our value of 537.4. Right, that's going to give us our value of the amount of energy that an earthquake has when it measures a 3 on the Richter scale. All right, and then obviously the next step there was to take the difference between, our 2 Richter scale versus our 3. So again, that would be where we subtract our 5, can't remember what it was exactly, 570 something, by our 17.3 here. Okay, if we look at an even stronger earthquake, and we're trying to ask the same thing here, okay, if you have a 7 on the Richter scale, it's going to follow the same exact process here. Subtract the constant, divide by the coefficient, use our definition, divide by that coefficient, and plug it into our calculator here. And what we would do here is we would take this value and we would subtract that 17.3 to see the difference. And what they're saying is it is 29 million times more energy. It is 29 million times more energy than a 2 on the Richter scale. All right, it is a very, very large difference between the amount of energies there. Okay, so again, a real world example of these logarithmic functions in action here. Okay, We'll take a minute and we'll finish up this study sheet here. So again, understanding that our log and our exponents are inverse functions of each other. All right, and for this one, the key is get the logarithm on a side isolated by itself. Okay, so that's all we're asking to do is get it by itself. Once you've got it by itself, you use the definition of the logarithm to write it in the equivalent exponential form, right? And then you just plug it straight into your calculator. Or as we saw in that last problem, we had to do another division to isolate our variable. But once you've done that, you can plug it into your calculator here. All right, a couple really good problems for you to work through here. And then a reminder of our earthquake problem here. All right, so again, this is the example where we had an extra step here because our value inside is not just an x value, it had a coefficient in front. So once we isolated our x value, once we isolated our logarithm, right, we then changed it using our definition, and then we had to divide both sides by that 0.37 in order to get rid of that coefficient out in front. All right, so then looking at our checkup here, all right, looking at our checkup. All right, all of these are just going to be solve and evaluate, right? Solve and evaluate. So you're going to do the same process. Again, I really suggest at least pick, 2 from each row here. So go 2 up here, 2 up here, and 2 up here. All right, try a couple of these problems before you go to your quiz here. All right, and you'll have this one quiz. Okay, so just to summarize what we've gone over today, all right, we went over 3.7, and that's talking about all of those different properties, right? How to combine and simplify our exponents and logarithms, okay? So we went over all of those different properties here. This is obviously the really meaty unit in today's lecture. So please make sure that you take some time to go over this tonight, especially before you do your 3 quizzes that you have that are assigned. Okay, for 3.8 here, okay, that was then using those properties to solve for our exponential equations, right? And undoing those exponential equations, and you've got 1 quiz there. And then on the flip side, solving our logarithmic equations was the last one. So for tonight, technically you have 5 quizzes, okay? And obviously if you're trying to keep up and not have a lot of homework, right, you would do this tonight. Because tomorrow, what's gonna happen is at about 8 a.m. I will release the lecture for the weekend, all right? And it's going to include 3.10 and 3.11, right? It's gonna include 3.10, 3.11, and obviously 3.12 here. So you'll have, for homework this weekend, you'll have the quiz in 310, the quiz in 311, and you'll have the test in 312, right? And that will finish up unit 3 for us. And then, like I told you, we're also going to start lesson 4. So we'll do 4.1 and 4.2 under statistical analysis. Statistical analysis. Okay. And as a reminder here, okay, I will be posting this lecture as a YouTube video, okay? Because I do put in like a natural stopping place, and I say, hey, stop the lecture, right? Stop and go and do all of this stuff for unit 3, okay? So we'll have that natural stopping place for you for this weekend, okay? But I don't care the pace at which you work, whether you want to do it, tonight and tomorrow, or you want to wait till Sunday night. I don't care. But my expectation is that you're going to have all of that work up to speed and up to date on Monday morning when we start class here for our last week of Zoom meetings with classes. So yay. All right, so make sure, work really hard this weekend so that next week is we continue to keep rolling here, okay? Somehow we ended a little bit early, so I'm not going to hold you here. Okay, I'll give you this time, obviously, for my sophomores. You can get started on that work here if you want. Juniors, you'll have just a little bit longer period between your breaks. Okay, so juniors, I'll still see you guys at 10 o'clock here. All right. Other than that, guys, if you have questions, comments, concerns, please reach out to me and I will help as best as possible. All right, have a great weekend and I'll see you guys later. Goodbye, goodbye.